Welcome to what I hope will be the last tutorial of topic 3, Formulae, stoichiometry, and the mole concept. So we just have our final learning outcome remaining, which is calculations related to percentage yield and percentage purity. So before we move in, so percentage yield and percentage purity. So there are cases where the amount of product you expect from a certain reaction does not match in reality. Like, for instance, sodium plus. Let's stop using sodium all the time. Let's just go for calcium. Calcium plus hydrochloric acid. I'm giving the 2 here because I'm balancing. You'll need it. You'll see soon enough. Calcium chloride plus H2, right? I'm not including the state symbols since they aren't required momentarily. So I just balance. This reaction is completely balanced since calcium 1, chlorine 2, and 2 hydrogen. Everything is balanced, so looks cool. Next, so for instance, you're told that you have 80 grams of calcium with you, of calcium powder with you. Now from 80 grams of calcium, which is equivalent to like mass by AR in this case, which is mass by AR of calcium is 40, so which is 2. So basically 80 grams of calcium means having 2 moles of calcium. So from 2 moles of calcium we may expect, or since 1 mole of calcium produces 1 mole hydrogen gas or 1 mole calcium chloride, we can expect 2 mole calcium to produce 2 mole hydrogen gas and 2 mole calcium chloride as well. But unfortunately that's not always the case, because in reality, and this will be 4, because in reality no reagent or no reactant is 100% pure, right? There are impurities in all reactants, right? So due to these impurities, you don't always get the desired amount of product you had calculated, right? Or your theory suggests, right? You'll be getting a lesser amount than that. So for instance, you might expect to have 2 moles of H2, or like 24 into 2, which is 48 dm cube of hydrogen gas from 2 moles or 80 grams of calcium. But in reality you'll be getting a lesser volume, which is, for instance, you'll be having 40 dm cube of hydrogen gas in reality. So this is the amount you had expected, and this is the amount you have received, right? So the amount you had expected is known as theoretical yield. I'm not going to that again. Theoretical yield. And this 40 dm cube, the lesser amount that you receive in reality, is known as the actual yield. Actual yield, right? Actual yield, right? So what do you do with these, right? So you basically calculate so basically there's this term called the percentage yield, which is nothing but a percentage calculation of how much you have received compared to how much you are supposed to receive, right? So the amount you have received is 40. The amount you were supposed to receive is 48, right? Right? So this is your actual yield, and the denominator is your theoretical yield, just 100%. And whatever you end up having here is your percentage yield of hydrogen in this particular reaction. So we have 40 divided by 48 is basically 83.3. So we can dismiss it by writing it 83%, right? So 83% is your percentage yield of hydrogen in this particular reaction, right? So you only receive 83% of the amount you are supposed to receive, right? Theoretically, you receive only 83% of the amount you were supposed to receive theoretically, or you receive the 83% of the amount you were supposed to receive, the yield you were supposed to receive theoretically. So percentage yield is nothing but a comparison of a comparison between the amount you receive and the amount you are supposed to receive. So that's it. We're done with percentage yield. So the percentage yield will not be the same for calcium chloride, though. It might be different. It might be quite different, right? Now we'll use the same example to learn about another quantity, another term. To learn another term, it's known as percentage purity. Purity. So using the same example, see, you have received a lesser amount of product than you were supposed to receive, right? Which clearly indicates the presence of impurities in your reactants, right? The fact that you received lesser amount of product than you were supposed to receive only proves that you had impurities, only confirms the presence of impurities in your reactants, right? So now you may ask, how pure are the reactants that we're using, right? So for instance, your question will be telling you which reactant has an impurity in it, right? So you'll be told that an impure sample of calcium is reacted with an excess of hydrochloric acid to produce all that, right? So you'll be told, or you will be made aware about which reactant has impurities in it, right? So you need not worry about you need not be confused about which reactant might have the impurity, right? So you'll be told about it. You'll be instructed about it. So the fact that you received only 40 dm cube of hydrogen gas when you were supposed to receive 80, so when we were supposed to receive 48 dm cube of it, only proves that there are impurities in your reagent. Now, say they tell you that the calcium sample that you have is impure, right? They tell you that an impure sample of calcium is taken. 2 moles of an impure sample of calcium is taken, right? Now you're asked to calculate the percentage. The question asks you to calculate the percentage purity of the sample of impure calcium that you have, right? So what do you do in that case? What you do is, just like your percentage yield, you calculate the actual purity, or the actual amount of actual mass, or the actual amount of calcium present, divided by the amount of samples been provided, and then multiplied by 100%. So basically, right, so Right, so first off, we were supposed to receive 48 dm cube, right? But we had received only 40 dm cube of hydrogen gas, right? Let's just take a look at what this means in terms of moles. That is, how much hydrogen gas had we received, how much hydrogen gas had we obtained in terms of moles, right? So as we know, any gas under room temperature and pressure occupies 24 dm cube volume. So 24 dm cube is occupied by I shouldn't write all that. So 24 dm cube is occupied by 1 mole. So 40 dm cube should be occupied by 40 by 24 moles, which is 6. This is not going to be a pretty number. It'll be 1.67. Not a pretty number at all. So 1.67. So in cases such, I suggest you just write it in, like, in these cases I suggest you write it in a fraction, right? So 5 by 3. We won't write it this way. We'll be writing it 5 by 3 in fractional form, just to make your calculations accurate, right? Just to ensure your accuracy. So just to maintain your accuracy, we will be writing this in fractional form, 5 by 3, right? So 5 by 3 moles of H2 had been formed in reality, right? Whereas you should have received 48 dm cube, or 2 moles of H2. You had only received 5 by 3 moles of H2. Now, calculate the number. Since we can calculate the number of product produced from the number of reactant, from the amount of reactant, we can do it the other way around as well. You can calculate the amount of product, the amount of reactant used or needed to produce a particular product. So you can always calculate the amount of calcium that reacted to form 5 by 3 mole hydrogen, right? So it's easy. Since 2 mole hydrogen reacts with 2 mole calcium, we can say 1 mole hydrogen reacts with 1 mole calcium, right? 1 mole hydrogen reacts with 1 mole calcium. It's a 1:1 ratio. So 5 by 3 mole HCl will react with 5 by 3 mole calcium, right? So basically this indicates that you only had 5 by 3 moles of calcium in your impure sample of 2 mole calcium, right? So you only had 5 by 3 mole calcium, whereas you were told that you had 2 mole whereas the impure sample had 2 moles, right, in it. So basically the amount you actually have is 5 by 3, and the amount you have in total, which is 2, you just multiply by 100% to get your percentage purity, right? So it's once again 83%, right? So yeah, so this is how pure your percentage, this is how pure your sample is. This is how pure your sample is, right? So yeah, so that's it. This is how pure your sample is. So you just write the amount that actually reacted, or the amount that was actually present in your sample, divided by the mole of your impure sample, and then multiply it by 100%. Alright, so there's something I forgot to mention here. which is the reason why our percentage yields and purity have turned out to be the same. What you need to do here is you need to use masses here and not moles, right? So you need to convert. You need to use, in case of percentage yield as well. In percentage yield, as we had seen, you put your actual yield on top. You need to convert it to your mass. So 48, we had 40 dm cube, which was our actual yield, which was which is actually 40 dm cube means 5 by 3 mole, right? Just convert 5 by 3 mole to your mass. So 1 mole of hydrogen gas has a mass of 2 grams, since there are 2 hydrogens here, multiplied by just mass equals moles mr. So mass is so this is mr actually. These are mr. So mr into mole. So our mole is 5 by 3, right? Divided by the theoretical yield, which is 48 dm cube, which is like 2 moles, right? 48 dm cube means 2 moles. So below we'll be having mr, which is the same 2, in multiplied by mole, which is 2 again. So we can eliminate these two, and our result. Oh, so there's a 100% here as well, into 100%, right? So our percentage yield is gonna be is gonna be 83%. And our percentage purity is gonna be something else. Our percentage purity will be since here we have our calcium, so we need the mass here. For instance, is 40, and here's is 40, right? So we can eliminate both and actually end up with the same results, 83%, right? So this is our answer of percentage yield and percentage purity. So I hope that's clear. And so basically this marks the end of our chapter. This marks the end of our chapter, percentage yield and percentage purity. We're done with our percentage yield and purity, so our chapter is now over, and I hope this has been useful to many of you, if not all. And I hope you got all that. I hope I've made all that clear, and thank you for bearing with me, and have a good day.